Our next speaker is René, who will tell us about the downgrading semantics of memory safety.
Yep. All right, thank you very much. So this talk will be about memory safety, or rather providing a semantic framework for thinking about memory safety. It will not be about memory safety in C. It will be about using ideas and techniques from secure information flow to define what memory safety means for small programs written in a small memory unsafe language called NOTAG, with a flat memory hierarchy, integers for pointers, manual memory management using malloc and free. So let's look at a small example. This small program allocates 128 bytes, or tries to allocate 128 bytes. It then proceeds by dereferencing the first of these allocated addresses and printing the content at this address. So is this program memory safe? No. First of all, the allocation might actually fail, right? So in that case, malloc returns a null-pointer. And this null-pointer may then be dereferenced, leading to a null-pointer dereference, which may then lead to a seg fault, and so on and so forth. Second of all, even if the allocation is actually successful, the output of the program still depends on uninitialized memory. Of course, the newly allocated memory may or may not be initialized. That actually depends on the implementation of the allocator. So I hope we can agree that this is definitely memory unsafe, but that of course begs the question, what does it mean to be memory safe? And if we look in the literature, memory safety is often, not always, but often defined as a long list of bad behaviors, errors, error classes that should be avoided, that should not occur in a memory safe program. So things like buffer overflows and use of uninitialized memory and so on. So if you want to prove that your program is memory safe, you would have to separately prove that it doesn't have any of these errors or error classes or bad behaviors. And of course, this is far from ideal. In fact, as noted by Michael Hicks back in 2014, actually this goes back way further, of course, but on his blog in 2014, he noticed that it would be really nice to have a definition of memory safety that would rule out these errors, bad behaviors as a consequence of the definition, rather than as building it into the definition. So let's explore that a bit further with the next example. So this example allocates two small buffers, 8 bytes, something like that, and then compares the actual addresses returned by the allocators, right? Depending on those actual addresses, it'll print either a 1 or a 0. So this program doesn't have any buffer overflows. It doesn't use any uninitialized memory. It doesn't have any use after free, and so on and so forth. So by this, by the traditional definition, this would be a memory safe program. However, the observable output from the program actually still depends on the actual allocator implementation. As I just mentioned, it actually depends on the concrete values, the concrete addresses returned by the allocation. So that means that the thing, if we wanted to reason about the behavior of this program, that would actually be really hard if we wanted to do that without taking the allocator implementation into account. So if we wanted to reason about the behavior of the program, we also need to reason about the behavior of the allocator. And we think that that for a memory safe program, we shouldn't really have to reason about the allocation. We should be able to reason about the program at a sort of an API level instead. So that leads to the sort of the key idea of our paper, is that a memory safe program is really a program that doesn't depend on the implementation of the allocator that it's using, right? So how do we formalize this, and how do we reason about this kind of independence? Well, that's I think the key insight of the paper is that we can look to the rich literature of information flow security and then borrow everyone's favorite security property, noninterference, right? Noninterference has been used for literally decades, reasoning about how program behavior, observable program behavior, is independent of any secrets held by the program. So we want to tap into this literature and then think of allocators, or rather allocator implementations, as secrets. And we don't want any of these secrets to leak into the behavior of the program. So we want to show some kind of non-interference result for programs. All right. So how does this look? Again, non-interference is about observable behavior that should not depend on something, secrets or allocators or whatever. So on the right-hand side, we have a small program that does an allocation and then immediately prints the address that is returned by the allocator. It doesn't really matter if it's the null pointer or not, it's just it's printing the concrete value, and this corresponds to a direct leak in the information flow security sense of the word that we have on the left-hand side, where the secret that is input from Alice is directly sent on to Bob, so Alice's secret is leaked directly to Bob. Yeah? Slightly more complex example. So this is the example from before. We have on the right-hand side, the control flow of the program depends on the actual addresses returned by the allocator. So here we have some kind of indirect dependence, right? This change in control flow is observable by the program, by the observable behavior of the program. This corresponds to an indirect flow in the information security world, where on the left-hand side again we have the control flow of the program actually depends on the values of the secrets, and this change in control flow is observable by an attacker by just looking at the output, right? So finally, a non-example, because now we have on the right-hand side, it's a slight change from the program before. I don't know if you noticed, but now this program on the right-hand side, it prints 1. No matter what is returned, no matter what the result is of this comparison of the addresses, the observable behavior is the same. And of course, we want our notion of memory safety to be precise enough to actually capture this as a memory safe program, right? So this is what makes our definition semantic. Also corresponding to exactly the same semantic notion on the information flow side, where again, yes, technically the control flow depends on the secret values, but the observable behavior actually doesn't. So we consider this to be a secure program and a memory safe program, respectively. All right. So now that I have hopefully convinced you that allocator independence is quite useful and probably a good idea for talking about memory safety, let's see where it doesn't work anymore. So on the program on the top right-hand side, we have a program that allocates probably a large buffer or something like that. And of course, this may fail, just like any memory allocation. But this program does the right thing. It checks whether or not the allocation fails. In that case, it prints an error message. Otherwise, it prints OK and is on its merry way. So this is obviously not an allocator-independent program, because depending on the concrete values returned by an allocator, it will either print an error message or it'll print OK. However, we consider this to be a memory-safe program. We really like, for our definition of memory safety, to also include this kind of programs, because we don't think of out of memory as necessarily a memory safety issue, especially not if it's handled correctly in the program. So how do we weaken our notion of non-interference just enough to actually capture these programs, but not any of the unsafe programs? Another example is the lower one on the right-hand side, a small program that, again, it allocates some memory, then it casts the pointer to an integer and prints the integer. Clearly not an allocator-independent program. However, if you're programming low-level systems like device drivers or for embedded systems, you very often have to work explicitly with specific addresses, right? So maybe you're doing memory mapped I/O, or you're setting up interrupt tables or whatever. So again, we would like for programmers to be able to slowly, gradually, in a controlled manner, break this independence. So make the program enable the programmer to say, yes, I know I'm introducing a dependence on an allocator. However, I know what I'm doing, so go away. And of course, still have, yeah, that's naive, I know, but at least we should allow them. But still retain memory safety, allocator independence for the rest of the program. So how do we manage this kind of weakening of our property? Well, again, we look to the information flow security community and look at the concept of declassification or downgrading. So noninterference says that a program's observable behavior should not depend on any secrets unless they have been declassified, because then they are no longer secrets, of course. So this idea of managing and controlling when and where to actually declassify, and of course there's a lot more to declassification, I will not go into that. But the idea here is that we're going to consider the cast to be a declassification operator. So this allows the programmer at least to manage when and where to weaken the memory safety guarantees, and sort of in the same way also for the out of memory. Right. So with all of these puzzle pieces in place, I'll introduce the no-tag language in a slightly more formal way. So it's a small while language. It doesn't contain any real surprises. It's C-like. Of course, it is not C because we don't have any undefined behavior as such, and we don't want to get into that discussion at all. That's not what this is about. But provide a framework for talking about memory safety in a slightly wider context. So the only thing we've added and observed, this is just a way of encoding the observable behavior. So this generalizes the prints and the outputs and network communication, whatever you need. Cast is basically a no-op. Is a no operator, and this is actually also the same in the information flow security community. A declassification operator, it's useful for indicating this is where it happens, this is where stuff happens, but it is a no-op in a semantic sense. Our language is, of course, parameterized on an allocator. Allocators define the semantics or implement the semantics for free malloc and then the null pointer, the exception pointer, right? So what is an allocator? In our setup, it consists of 5 things. It has an abstract allocator state. We don't really require anything of this state or have any constraints for it. It's up to the allocator to decide what to use it for. We just make sure to actually thread it throughout the semantics so that it's available. And then, of course, it defines a null address, malloc, and free, and also an initialization that is only run once at the beginning of the program to set up the initial allocator state. Okay, semantics. Nothing too exciting. I'm not going into any depth with that. Just note that the semantic step relation, of course, depends on an active allocator. That's the alpha on the left-hand side of the turnstile. We thread, as I said, the allocator state. That would be the capital A and the A prime. And finally, running the semantics generates an event trace. Events are the things that might happen during execution that are of relevance to our memory safety. So that would be all of the normal memory management instructions. Do note that there is an mfail which corresponds to, okay, I've tried to do a malloc, but it failed. I tried to allocate n, size of n, memory allocation of size n, but it failed. So we want to keep track of that, of course. And the ops v is, of course, sort of the event corresponding to an observe instruction, right? So these are the externally observable this is the externally observable behavior of the program. So running a program gives rise to an event trace, and this is really what is at the heart of our formalization. So how do we formalize this kind of non-interference? I'll not go into a lot of depth with that, but we'll be more than happy to talk about this after the presentation. We use an epistemic approach, so that kind of turns the idea of thinking about non-interference on its head, if you're not used to it. So instead of thinking of what can be observed, we're actually thinking about what does an attacker know, what is the precision of the knowledge that an attacker may have about the system. In our case, what we are thinking of is what is the set of allocators that would give rise to the same event trace for this program. So basically, this is the set of allocators that we can't really distinguish based on the traces that we've seen so far. Yeah. So the idea for memory safety would then be this set of allocators should be, if not constant, it certainly shouldn't become smaller over execution time, right? So the more we observe, it should stay the same or certainly not grow smaller, because if we can remove an allocator from this set, it means we've actually introduced a dependency, because now we know that it cannot no longer be this allocator. Formally, we define the allocator impact. This is the blackboard A for a command C, for a program C that generates a trace T. So Imagine we've run the program C and we've observed the event trace T. Now the allocator impact is the set of allocators that would have given rise to exactly the same trace, basically. Okay? So now, as I said, the idea is we want to make sure that this doesn't really change. That's fine, but we also need to take care of our downgrading operation. So in this case, the cast operation. In order to do that, we rely on some fairly sort of a weakening of the idea of an allocator, of the allocator impact. So we're going to define this blackboard A cast arrow, whatever, to mean more or less the same as the allocator impact, except that it's the set of allocators that would give rise to the same trace, but also furthermore allows for a further cast operation, for a further cast instruction. We make no requirements of what are the addresses that gets cast, so what are the specific values used, but it should be possible to do a cast after having produced the trace T. Same goes for the allocator. So how do we use these allocator sets to actually define the non-interference? Well, if we start from the bottom, that's probably the easiest. So the blackboard A, so the allocator impact for the trace T eta, right? So this is the set of allocators that are able to actually produce the trace T, combined or followed by a single eta event. This should be the same as the set of allocators that could produce the trace T. So what that means is that even though we've seen yet another event and we've observed something about the program, this eta, we can't actually remove any of the allocators from the allocator impact sets, meaning we haven't introduced accidentally or on purpose any dependencies on any of the allocators in this set. Yeah. For the cast operation, this is slightly different because we have to take a slightly weaker definition. So what we're requiring here is that the allocators that have given rise to the current set of traces must be part of, again, this progress impact for cast, which says that yes, it's the same allocators, but all of the allocators in this set must also be able, so all of the allocators that have been able to produce the trace T must also be able to produce some kind of cast operation. Again, we make no requirements on the values that are actually cast or the addresses that actually are cast, but they must be able to do a cast operation. I'm running out of time, so I'll just skip this, just briefly mention that we've used as a use case for this idea, we've shown that we can translate the memsafe language of Amorim, Rydhof, and Pierce from their post-2018 paper into our no-tag language and preserve memory safety. So memsafe language is, of course, a language of memory-safe programs. So this translation actually satisfies our gradual allocator independence, i.e. memory-safe. And in fact, the translation of memory programs that are not stock, so not errors out in some way, they will either be out of memory or they will succeed with the same memory. I think that's all I have.
There's a lot of questions, but I'm afraid we only have time for one or two quick questions. Could you get set up?
Thank you. I guess it'll be really quick. Hi, I'm McKenna McCall at Colorado State. I'm just kind of curious about maybe a philosophical question.
All right.
Why think about this from a confidentiality perspective instead of integrity?
That's a really good question.
It feels more like an integrity condition to me.
That's funny. I think more of it as a confidentiality because actually we don't want any information about the allocator implementation to leak into the program. So to me, that's confidentiality, but I think we could equally have formulated as integrity, actually.
Sure.
Yeah.
Okay. Yeah.
Thank you. Oops, sorry.
Your allocator, as it's currently formalized. Hi, I'm over here.
Hi.
May Milano, Princeton.
Yes.
Your allocator, as it's currently formalized, has a very strong, malloc-style API.
Yeah.
Most allocation that you see in C or low-level code is just immediate values. I'm going to stick something on the stack, and now it's memory. In your formalization, if you were to extend that to handle immediate values and then casting thereof into memory, would those all just be part of the allocator, or would those require a different kind of formalization?
So we haven't actually looked at stack memory or indeed at the sort of sub-object memory safety. I think stack is slightly different. We need a different setup for it. I think the basic idea is the same, but we need to identify more more places to apply this declassification. Because actually, I think there is something, when we copy things into the stack, that would correspond to some kind of declassification operator. But this is very much work in progress.
Okay, let's thank René and take work with overflow.